Butterbot version 3 log 4. Today we'll be going over the promised control theory portion of the bot. Now, technically, I work in a control theory lab, and that is a load-bearing technically. I went an interesting direction with this, and I'm going to try to explain the best I can how control theory works, what it is, and what it does to a layperson. But by the end of this, hopefully we'll be on the same page about the direction I took. Let's get into the beginning. As with everything, we start with math. Specifically, that math from that one video a long time ago where we got that huge differential equation. That differential equation was like this one, where an equation of position, velocity, and acceleration relative to some input describe the dynamics of the arm. Now, if you're unclear on those terms, the dot above the x and the double dot above the x here is indicative of the number of time derivatives. From physics, you should know, and if you don't, now you do, the derivative of position in terms of time is velocity, the derivative of velocity in terms of time is acceleration. So, we have a differential equation in the time domain that represents how the bot moves to a given time domain input. What do we do with this? Well, the first thing we do is we convert it to the Laplace domain, or the frequency domain, so we're not in time. Now you might be thinking, frequency is just the inverse of time. Invert the equation. No? Good thought. Kind of. Not really. What we do to do this is we have to do an S operator. In the simplest terms, how we convert to Laplace is using this Laplace transform for the differential equation polynomial. It gets more advanced than this, but this is typically what you end up working with most of the time. For every derivative you have, you're going to have an S operator times the Laplace transform of the function. So every xt is just x of s plus the initial conditions. Now, because we work in mechanics, you and I, we work in mechanical things, we get to do something great that a lot of our mathematician and electrical friends don't necessarily get to do. We get to say that, yeah, that's zero. It starts wherever is the most convenient for us, and that's almost always when that is zero. So we get to do that, because we're just better than them. Now moving on, we'll take this and we'll convert it to Laplace. And there you have it. You take since the initial conditions are zero, you take the x of s and the y of s, and you factor it out, and you just get s squared plus x plus 1 times x of s is equal to y of s. Now, we'll put a pin in this and start getting into control theory. But with this, you've now gone from calculus and into differential equations. Congratulations. Let's start with driving a car. If this were a better video, we would cut to an animation that would show visually everything I'm about to describe. However, we blew the budget on dustless chalk, and so you just have to listen to me and use your imagination. Now, you're driving a car, and you come across a red light, and you don't slam on your brakes, at least you shouldn't, and if you do, just stop watching this video because it's not going to make sense. But you don't slam on the brakes. You slowly depress the brake in so you come to a controlled stop to the stoplight. This is called active control. The brake is an actuator, and you gauge the distance between yourself and the red light and slowly depress the brake in the appropriate amount so that you can control the stoppage. It's your brain controlling your foot, controlling your car. If we were to convert this to, say, an electromechanical system, the brake would be the actuator, your eyes would be the distance sensor between your car and the red light, and then you'd have your brain, which is the controller, and where control theory comes in. How does a computer know to how much to gauge the force so that the car stops at the right time? You can do it because you drive a car a lot and you have experience in these sorts of things. You have a feel for your car and a feel for a brake. How do you tell a computer about what it should feel? Now, let's look at this example a different way. Your car is going a certain speed. From that speed, you use your eyes to measure the distance based off the velocity you were going. You notice the distance between you and the stoplight. You subtract that from the distance based off the speed to get the distance you have left before you reach the point where you have to stop. Gauging that distance, you apply a force to the brake, which slows down the car to where this velocity is 0. This is called a feedback loop. And while in our example, this is the car, this is your eyes, and this is the brake, in a generalized example, this is the plant, this is the sensor, and this is the actuator. With this being the input and this being the output. This is the most basic form of control theory, your negative feedback loop, and where most things are going to relate back to. Now, you might be wondering, how does this feedback loop relate back to our math? Well, each of these blocks is representative of a transfer function, which is something that's in Laplace. It's characterized by the output in terms of S over the input in terms of S. And what it does is you take the input function and you multiply it by this transfer function, and then you get the output. So it's a transforming of both functions, hence transfer function. How this relates to our previous dynamics, we converted that differential equation to Laplace. So we had s squared plus s plus 1 times x of s is equal to y of s. Using this is our input, this is our output. We divide, and to get x of s over y of s, we have 1 over s squared plus s plus 1. We have a transfer function that represents the dynamics of our body. Now, from what you could probably surmise by watching this equation would be the plant. It is our untransformed, unedited, all of those things for the robot. The actuator would be included in this, it would be the motors. And what we need to do is to design an extra block that would affect this transfer function so that we get the desired response in the time domain, and that's called controller design. Or that's what I believed. Let's start talking about real life now. So, the real system. We have the plant. It outputs a position based off an input. We can do a sensor in there. It'll be some sort of encoder. We can get a position and rotation, and then put that back in, loop it, design a controller, doing the root locus or something, and there. Controls is done. But not really. Because the plant isn't really the plant. You see here, the plant is the dynamics of the system. And with controls, we don't care about dynamics. No, we only care about controls. We're not controlling the bot. We're controlling the motors. And the motors have a plant that's determined by its own motor constants, like KV, relative to the voltage and the current. And we haven't done any math for voltage and current. It's all based off the circuitry, which should be very simple, but it's not. And so since we're controlling the motors, we need to get the motor constants from all of that stuff. But I take my motors off of garbage, things that I harvest, scrap, reduce, reuse, recycle, right? There's no documentation. I don't have the tools to measure those things. And so even if I did get the motor constants and relative to the voltage, so I can get the torque outputs and then be able to get an actual plant for the motors I'm controlling, I have 3 motors. Which means I need to do branching outputs. So not do I have 1 feedback loop, I've got 2 and 3 stacked on top of each other, with them feeding into each other with an internal feedback loop, and from that, that's where the dynamics comes in, because the output from one is relative to the input of the other, which delays the system. But let's say I do that. I get all that math, I get the plant, which is gigantic, and then I design a controller doing the root locus or the transformation matrix or whatever method you want to do with it, and I get it done. Now what? Well, now I have to program it. How do you do that? Because you can't do it in Laplace. You can't program in Laplace. Laplace is continuous. For you electrical people, that's called analog. You know how that doesn't exist, really? Not for anything nowadays. You need to convert that to discrete. And converting that entire thing to discrete really just means that you start over, not in Laplace, but in discrete form. And all of this is just a long way of me saying that I didn't do this. I'm gonna plug in a joystick. Up is left, down is right, and the other direction moves the other motor. And I'm gonna have a button that rotates the end effector. So, end of lecture, don't do controls. Until next time.